Objectify Technologies is an additive manufacturing engineering service provider with expertise in metal and polymer additive manufacturing, with machinery and post-processing under one roof. Welcome to Objectify AddMics podcast, a conversational event for engineers, industrialists, and just anyone with a knack for additive manufacturing. For more info, visit us at objectify.co.in.
Dr. Kumar, could I please have your brief views on the topic of materials for additive manufacturing?
Yeah, from the materials point of view for additive manufacturing, my experience and expertise limited to metal additive manufacturing with different additive manufacturing processes. So, from that perspective, I'll discuss what I think might be useful to the audience. So, like you mentioned in your presentation, there are two different regime of material development. So, one is something that the alloy is currently being used and practiced using different manufacturing processes like casting or forging a type of alloys, but now people wanted to manufacture components with complicated design, so they wanted to make a feedstock out of that particular alloy. So when you try to convert such alloys, since the process changes and the process dynamics changes, so it may not be fruitful to extract an alloy composition within everywhere within the window of the specification of particular alloy. So we need to optimize and develop the chemistry within the specification at the same time without sacrificing the properties. At the same time, we should be able to print or deposit in any of the additive manufacturing process. So this is relatively not so challenging process, but when compared to the development of new alloy chemistries for additive manufacturing. So one of the reasons why people try to generate or develop new alloys in additive manufacturing is because they want to achieve better properties than whatever the current alloys offer, or they're trying to increase the printability or printing efficiency. So they wanted to come out of the current alloy specifications and try to develop. So during this process, there are several challenges with respect to the metallurgy and the process, the printability aspect and the property aspect. At the same time, we also have a problem with qualifying the material for certain applications. So when it comes to the implementation of additively manufactured components, since we are trying to change the process, so that is an uphill task, and also if you're changing the material, trying to implement a new material, that is additional burden that somebody has to overcome. So these are the practical challenges. So when it comes to qualification, testing and characterization plays a major role. So for qualification purposes, there is an enormous amount of testing and characterization needs to be done if you're trying to implement a component for aerospace applications. So there are particular guidelines which need to be followed in order to come up with the A basis value, B basis value to implement a certain material that are developed for additive manufacturing. So this is the same process for developing materials for any other manufacturing process, but when it comes to additive manufacturing, so the industry is relatively small, and the market base for such a material could be small. So the cost of testing and qualification can be very high compared to the market size for that particular alloy that is being developed. That's the real challenge right now.
Drivers of selection of AM processes and materials for additive manufacturing?
From the technical point of view, obviously, so the person who wants to achieve something that is not being done currently won't consider the cost of this alloy, right? So people are expected to be highly technical, but when it comes to applications in aerospace and all, so the performance matters the most, and also the trade-off that we can get by using additive manufacturing in terms of performance. That trade-off is highly inclined towards getting better properties and better performance. So that can be easily justified for the increased cost.
Yeah.
So when it comes to new material development, there are two aspects, right? So one is completely new material for the entire material spectrum. So sometimes when new material is referred in additive manufacturing, it's already an existing alloy trying to convert into additive manufacturing feedstock. So that is a little bit different, probably could address too. So for example, so some of the high temperature alloys like 939 or 738, the internal families are already existing alloys. They are they are prone to cracking when it is printed. So now people are trying to develop those materials. So that also falls in new material category within additive manufacturing.
We've touched a lot on the post-processing. So could you discuss a bit on the post-processing methodologies that would enable a high fatigue and creep characteristics for metal AM parts?
Sure. So as far as post-processing is concerned, is like so in order to remove the porosities we hit, and then in order to get the right microstructure, so we do certain heat treatments, either solutionizing, just solutionizing and or annealing, or so in some cases we do solutionizing and aging. So particularly if you want to get certain properties, so the properties are manifested based on the microstructural condition and the chemistry, right? So when it comes to material properties, so when it comes to AM materials, it is a little bit different than conventionally manufactured material. The material is not having the uniform microstructure. It has the microstructure develops based on the cooling rate. So the cooling rate basically is the cooling rate, not only the cooling rate and also the solidification structure. So wherever the thickness changes or the cross-section area changes, the thermal condition can be different. So due to which the microstructure within the part is heterogeneous. So one has to look into it. So when you're designing your heat treatment or post-processing, so we'll have to find an optimal the heat treatment cycle. So this heat treatment cycle may not be the current the ASTM specified cycle or any other standard heat treatment cycle which are mentioned in the handbook. So particularly if you want to get a high creep resistant material, so try to avoid the phases that are deleterious to the high temperature properties, and try not to generate at the grain boundary carbide. Try to minimize it. at the same time. So you need to have a certain size and distribution of certain type of carbides within the matrix uniformly distributed. So these kind of things provide the challenging to AM material because the microstructure is heterogeneous. You're trying to optimize the microstructure in one location that may not be replicated all over the place. So the ideal situation in this case is try to find where the critical location of the component is, try to optimize the microstructure wherever it matters the most. And also, I still believe that the additive manufacturing is the lowest hanging fruit for new material development. So even though it has industry specific barriers, but if not, so in additive manufacturing, so in any other developing new materials in any other technology is going to be even more tougher. So I think there is enormous advantage we have in additive manufacturing in terms of testing small quantity of material and so on. So with that, I thank, and also I learned a lot from Dr. Banerjee and Dilip's comments as well.
Thank you very much. This is me signing out, Vrigu Ahuja, CTO of Objectify Technology.